Hi, my name is Lickett bearing a roll number 21BQ1A05M3. Today I am here to explain you about the Turing machine. Turing machines, first described by Alan Turing in Turing 1936-7, are simple abstract computational devices intended to help investigate the extent and limitations of what can be computed. Turing's automatic machines, as he termed them in 1936, were specifically devised for the computing of real numbers. They were first named Turing machines by Alonzo Church in a review of Turing's paper, Church 1937. Today, they are considered to be one of the foundational models of computability and theoretical computer science. Turing introduced Turing machines in the context of research into the foundations of mathematics. More particularly, he used these abstract devices to prove that there is no effective general method or procedure to solve, calculate, or compute every instance of the following problem. Entscheidungsproblem problem, the problem to decide for every statement in first-order logic, the so-called restricted functional calculus. See the entry on classical logic for an introduction, whether or not it is derivable in that logic. Note that in its original form, Hilbert and Ackermann 1928, the problem was stated in terms of validity rather than derivability. Given Gödel's completeness theorem, Gödel 1929, proving that there is an effective procedure, or not, for derivability is also a solution to the problem in its validity form. In order to tackle this problem, one needs a formalized notion of effective procedure, and Turing's machines were intended to do exactly that. A Turing machine then, or a computing machine as Turing called it, in Turing's original definition, is a machine capable of a finite set of configurations. Q. 1. Q. N. The states of the machine, called M configurations by Turing. It is supplied with a one-way infinite and one-dimensional tape divided into squares, each capable of carrying exactly one symbol. The machine is an automatic machine, which means that at any given moment, the behavior of the machine is completely determined by the current state and symbol, called the configuration, being scanned. This is the so-called determinacy condition, section 3. These A machines are contrasted with the so-called choice machines, for which the next state depends on the decision of an external device or operator. Turing 1936-7, 232. It was proven by Shannon that any Turing machine can be reduced to a binary Turing machine. Shannon 1956. Turing, in his original definition of so-called computing machines, used two kinds of symbols: the figures, which consist entirely of zeros and ones, and the so-called symbols of the second kind. These are differentiated on the Turing machine tape by using a system of alternating squares of figures and symbols of the second kind. One sequence of alternating squares contains the figures and is called the sequence of F squares. It contains the sequence computed by the machine. The other is called the sequence of E squares. The latter are used to mark F squares and are there to assist the memory. Turing 1936-7, 232. The content of the E squares is liable to change. F squares, however, cannot be changed, which means that one cannot implement algorithms whereby earlier computed digits need to be changed. Moreover, the machine will never print a symbol on an F square if the F square preceding it has not been computed yet. This usage of F and E squares can be quite useful, but, as was shown by Emil L. Post, it results in a number of complications. There are two important things to notice about the Turing machine setup. The first concerns the definition of the machine itself, namely that the machine's tape is potentially infinite. This corresponds to an assumption that the memory of the machine is, potentially, infinite. Thank you for watching. Thank you.